Hey everyone, so now I'm going to work through an example problem, which is a combination of a pH problem. So how you would figure out the ratio of CAPS acid to base in a particular buffer, and then how a reaction would deplete the base to form the acid form. Okay, so we'll go ahead and go through it. So the question is, based on your highest activity value, which we determined from our previous problem in this handout was 0.045 units, how many minutes would the reaction proceed under an effective buffer if the buffer 50 millimolar CAPS pH 10 was used? You must show your work to receive full credit. So we have that our maximum activity value is 0.045 units. We use 2 milliliters of an assay mix, and then we have we add 0.03 mils of LDH, or 30 microliters, and that's for a total of 2.03 mils for assay mix plus LDH. And then that assay mix contains 2 mils of 50 millimolar CAPS buffer at pH 10. Remember, CAPS is a pKa of 10.4. And then we add a half mil of 150 millimolar lactate, a half mil of 6 millimolar lactate for 3 mils total. So we'd make up the buffer exactly like you would for your activity assay, except in this case we would just take 2 mils to monitor instead of 1. Okay, so again we have 50 millimolar CAPS at pH 10. So to solve this problem, we need to find the moles of total CAPS. So this is CAPS, acid, and base. And we can get this from the concentration of CAPS and the volume added. Okay, then once we know the moles of total CAPS, we can find the ratio, of CAPS acid to CAPS base. And then we can solve for the ratio at pH 10, which is where we start, and then at pH 9, because the effective range of a buffer is the pKa plus or minus 1. And so for CAPS, or I guess that would be 9.4, and for CAPS, this pKa is 10.4. So 10.4 plus or minus 1 is 9.4 to 11.4. Now our reaction is going to produce protons. So as the reaction progresses, the pH is going to decrease. So that means we would be approaching the limit of 9.4 rather than 11.4. So to figure out the pH change that would happen, for which this would be an effective buffer, it would be the change in pH from pH 10 down to 9.4. So we can use the ratios, see how the ratio of acid to base changes, and then therefore the moles of each changes from a pH of 10 to a pH of 9.4 to figure out the change. So then once we've straightened out, so essentially that would tell us how many micromoles of proton must be produced, or moles produced, to change from 10 to 9.4. So then we know how many micromoles of, pyruvate, NADH, NH+ must be produced to move the pH from 10 to 9.4. So then we have to figure out the time. So if we know the units, which is micromole per minute, we can solve for the time required to generate the protons needed to convert from 10 to 9.4, and then that would give us the length for which our reaction would proceed under an effective buffer. All right, so let's start by figuring out how much CAPS we have. Okay, so in our assay, we have 2 mils of 50 millimolar caps buffer, we have 0.5 mils of 150 millimolar lactate, and we have 0.5 mils of 6 millimolar NAD+. And actually, for simplicity's sake, we're going to make the assumption here that, let's say we do our math, so that this 2 mil of the assay mix is 50 millimolar caps, just for ease of calculation. And so the way that to figure out how much caps you would have, we would say 2 mils, which is equal to 0.002 liters, times 0.05 moles of caps per liter. And that will give us 1 times 10 to the negative 4 moles. And that's a really small number to keep track of. So I'm going to say, let's convert this to micromoles. So you have 1 mole, 1 times 10 to the 6 micromoles. Because again, that prefix micro means 1 times 10 to the negative 6. And that gives us 100 micromole. So in our reaction tube, we have 100 micromolar caps, and that's total. And that's equal to the micromole of caps acid plus caps base. So the next step is, so in this amount of caps, it's going to remain constant throughout the entire reaction. We're always going to have 100 micromoles of caps in our reaction, in our assay. What's going to change is the ratio of how much of that is caps acid versus how much of that is caps base. So as we produce the protons, the caps acid, which is caps with an H on it, is going to increase, whereas the caps base, or just plain caps, is going to decrease. And so as the reaction progresses, that ratio is going to change, and it's going to shift to favor the protonated or the acid form rather than the base form. So the next step then is figuring out what are our ratios at pH 10 and then at pH 9.4. So let's start with 10. So this is where you yank out the Henderson-Hasselbalch. So pH equals pKa plus the log of the acid or of the base form to the acid form. So pH 10 is equal to 10.4 plus the log of the base form over the acid form. So we rearrange this to get negative 0.4 is equal to log of base over acid. Now we want to get rid of the log, which is log 10. So we take 10 to the both sides, and then that gives us 0.4 is equal to A minus over HA. And again, I'm going through this pretty quickly, but you can take a minute to pause and walk through this more slowly, or repeat or rewind as you need to. So then 0.4 HA is equal to A minus. So now that we have this ratio, we can go back and we can substitute that into the equation for the total caps to figure out how much of our caps at pH 10, how much of our caps is acidic, and how much of our caps is basic. So we have 100 micromole total. Total is going to be equal to X micromole of acid or base and X micromole of HA of the acid of the acidic form. Now what we do is we take the substitution. So we have here that 0.4 HA is equal to A minus, or 0.4 of the of caps acid is equal to caps base, and we can do a little algebra here, we can sub this relation in for the micromoles of caps base. And so when we do that, we get 100 micromole of caps is equal to 0.4 HA plus HA. We get 100 micromole caps is equal to 1.4 times HA. We can divide both sides by 1.4, and then we get that HA is equal to 71 micromole. So we know at pH 10 we have 71 micromolars of HA, and so to solve for A minus, the micromole of A minus would be equal to 100 micromole total minus 71 micromole HA, and that would give us 29 micromole of A minus. So at pH 10, we have 71 micromoles of HA and then 29 micromoles of A minus. So then the reaction is effective until a buffer of 9.4. So then what we have to do is we have to figure out what the ratio, or how many micromoles of HA and how many micromoles of A minus we're going to have at pH 9.4. So again, I want you to take a minute. At pH 9.4, are we going to increase the micromoles of HA? Are we going to decrease? Take a minute, write down your guess, and then I'll go through and we'll find out. Okay, so again, we use the Henderson-Hasselbalch, except at pH 9.4 is equal to 10.4 plus the log of A minus over HA, or caps base over caps acid. So -1 is equal to log of the caps base over the caps acid. Again, this is a log 10, so to get rid of the log, we have to take 10 to the both sides. And so then we get 0.1 is equal to the log of A minus over HA. So then we get rid of the log. We got rid of that with the 10 to each side. So then 0.1 HA is equal to A minus. So again, when we change pHs, we still have 100 micromoles of caps. It's just the ratio of acid to base changes. So again, 100 micromole is equal to A minus plus HA. We're going to substitute that guy in now, and you can see now that that ratio has changed. So 100 micromole of caps total is equal to 0.1 A minus, or HA plus HA. So 100 micromoles is equal to 1.1 micromoles of HA. We divide both sides by 1.1, and then we get 91 micromoles of caps acid. So then to solve for base, caps base, 100 micromoles of HA, of total, caps total, sorry guys, minus 91 micromole of caps acid gives us 9 micromoles of caps base. Okay, so if we set this up, I like to set this up in a table because I think it's easier to see. So at pH 10, okay, I used the highlighter setting there instead of the writing guy. Okay, all right. So we start off, so at pH 10, and then we go from 10 to 9.4. Oh, had a whole page, I didn't even know it. Okay, so if we start with, so caps acid, and then cap space. So this would be HA, and then A minus. So at pH 10, we have 71 micromoles of caps acid and 29 micromoles of cap space. Then at 9.4, we go from 71 to 91 micromoles of caps acid, and then down to 9 micromoles of cap space. And so if we look at the difference, we subtract the final minus the initial, so 91 micromole minus 71 micromole. That gives us a difference of 20 micromoles. So in this case, we're adding 20 micromoles. And in this case, for the cap space, we're losing 20 micromoles. So that means that for the reaction, so for the pH of the reaction to drop from 10 to 9.4, and this comes from proton production from the reaction, 20 micromoles of caps acid or base must be converted into caps acid. So that means 20 micromoles of H plus, and by extension NADH and pyruvate must be produced to make that pH changed. Okay, so the reaction has to run for the amount of time that would give us 20 micromolars, or 20 micromoles of H plus and NADH and pyruvate, and the time that it would take to produce 20 micromoles of each product is the time that the reaction would operate under an effective buffer. So to solve for this, we know that our reaction rate progresses at 0.045 units. And another way to write the units, 0.045 units equals, equals 0.045 micromole produced per minute. Again, remember, this is where it's really important to know your units, because your units are a key to being able to figure out how to solve the problem. So then the question is, if we multiply it by how many minutes to produce 20 micromoles? So then again, we invoke our algebra here. So the minutes is going to be equal to 20 micromole divided by 0.045. Okay, we'll just go ahead and we'll erase that because that looks kind of sloppy. My bad, guys. 0.045 micromole per minute, and that will give us 444 minutes. All right. So this reaction can run for 444 minutes in order before it reaches a pH that would be out of the buffer range of effectiveness. And what would this, does that mean that this buffer is effective for this reaction? I think so, considering 444 minutes would be several hours. So you could run this reaction for a long, long time without having to worry about the pH changing.